So moving on to example 2, we're going to continue using our calculator to solve for right triangles, given that we're only provided 2 of the 3 sides and 1 interior angle. So again, we want to make sure that make sure that our calculators are in degree mode. And I know I just changed mine to degree mode, so hopefully you guys have had a chance to change yours as well. So moving on to example 2, we're going to look at 2 more examples where we will be using our trig functions to help us solve for our missing side lengths. So again, I'm going to start off with writing SOHCAHTOA on the top of my paper. It helps me remember. So in letter A, I'm given the interior angle of 27 degrees. In relationship to that 27 degrees, 5 is my opposite leg. And the x, which is in relationship to my 27 degrees, is my hypotenuse. So the trig function that deals with opposite and hypotenuse is my sine value. So going back to what my sine value represents, sine of theta is equal to my opposite side over my hypotenuse. So if I fill in the pieces of information I know my theta is my 27 degrees. So sine of 27 degrees is equal to my opposite side length, which in this case is 5, all over my hypotenuse, which in this case is x. Just like I did in example 1, I'm going to stack both sides as fractions, and I'm going to cross multiply. Now in this case, when I cross multiply, 1 times 5 gives me 5 is equal to x times sine of 27. Just like I would deal with this situation in any other equation, these two, the x and the sine of 27, are being multiplied. So to get x alone, I'm going to divide both sides by sine of 27. So x can be found by taking 5 divided by the sine of 27. So let's plug that into our calculators. So again, you want to make sure that you are in degree mode. To check on that, you can go to your mode button. Make sure that you are in degree mode and not radian. So if you clear out of that, we're going to take 5 divided by, and then in parentheses, I'm going to take sine of 27 degrees. When I hit enter, I get x to be about 11.01 if I round. Moving on to letter B, we're going to find this x value of this right triangle. In this case, my theta is going to be the 54 degrees. So in relationship to 54, my x is going to be my opposite side, and my 12 is going to be my adjacent side. The only trig function that deals with adjacent and opposite, and I can go back to my SOHCAHTOA up top, opposite and adjacent is going to be my tangent. So to set this up, I know that my tangent of theta is equal to opposite over adjacent. 54 goes in for theta, which is given to me as tangent of 54, is equal to my opposite side length, which is x, over my adjacent side, which is 12. Stack both of them to be the same, cross multiply. 1 times x is x. 12 times the tangent of 54 is 12 times the tangent of 54. Use my calculator one more time. Tangent 12 times the tangent of 54 is equal to 16.52. So x is roughly 16.52. So why do we care? Why will trig ever be useful, or how will it ever be useful to us in the real world? Which is a pretty valid question. It's definitely something that we want to talk about. So here in example 3, I gave a pretty simple example of how this could be useful in the real world. So in example 3, you're given the scenario that your Career Center class is putting up the LCTC flagpole. The flagpole casts a shadow of 10 feet long. Viewed from the end of the shadow, the top of the flagpole makes a 63-degree angle with the ground. We want to sketch a diagram that represents the situation and find the height of the Career Center flagpole. So to start off, there's a couple pieces of information that we're given here that we're going to want to use. The first is, we know that we have a flagpole, so I'm just going to sketch. I'm not the best drawer, but I'm going to sketch a little flagpole, pole next to it. And the first thing we know is that the flagpole casts a shadow that is 10 feet long. So let's say the sun is over in the corner, and it's shining down on the pole, and let's say it casts the shadow, which is going to be this little dotted line. We'll call this the shadow. That is, from here to here, we know to be 10 feet long. We also know that the top of the flagpole and the end of the shadow makes a 63-degree angle with the ground. Now we want to find the height of the flagpole. So since we want to know the height of the pole, I'm going to call this side X, because that is obviously the height of the pole that we're looking for. So we know the shadow's 10 feet long. We know that the top of the pole and the ground of the shadow makes a 63-degree angle, and we want to solve for X. So in this situation, we obviously wouldn't be able to grab a big ruler and be able to measure this pole. So we're going to use trig to find the height of something that's a little too big to actually measure in real life. So in this case, if we go through, in relationship to my interior angle, which is theta, X is my opposite side, and 10 happens to be my adjacent side. Using my SOHCAHTOA, I know that the trig function that deals with opposite and adjacent is my tangent function. And my tangent function is the tangent of theta is equal to opposite over adjacent. So filling in the pieces that I know, tangent of my interior angle theta, which is 63, is equal to opposite over adjacent, which is 10 feet. Stack both of them so that they have the same structure, so they're both fractions. So we can put tangent of 63 over 1, and now we can cross multiply. 1 times x is x, 10 times the tangent of 63. If we plug that into our calculator, times the tangent, 63 degrees, gives me roughly 19.63. And since we're dealing with a real life situation, we're going to need our units. So since we're dealing with a shadow that is 10 feet long, we're dealing with the height of a pole that is going to be 19.63 feet high. So at this point, you have numbers 4 through numbers 17 that are attached to the same packet. So at this point, I want you guys to spend some time tonight going over these problems, numbers 1 through 16, actually 17, and see how far you can get. We're going to be working on the rest of these together in class the next time that we meet. One piece of information I do want to share with you is on this next page, it starts off with special right triangles. If you look down to the next part where it says evaluating functions, for some reason I don't think it printed on your PDF that is uploaded to Blackboard. So 7 should be sine of 23 degrees. 8 should be finding the values of cotangent of 15 degrees. And number 9 is having you find the value of secant of 67 degrees. So a couple key things I want you to pay attention to. 7 should be pretty straightforward for you, but cotangent and secant, before we talk in class, I want you guys to try to see if you can come up for these values on your own. You know what cotangent is, and you know what secant is. And I just want to give you a hint that you may want to think about what their reciprocals are and see if you can use that to plug into the calculator to get your values for numbers 8 and 9. Everything else is pretty straightforward, and we'll talk about the rest of these answers and any questions you may have the next time that we're in class together.